In this program, we'll be discussing what is being done to fight pollution. First, filtering processes for drinking water, then the purification of wastewater, and finally, pyrolysis under vacuum, a very promising technique for recycling solid wastes. Most of the major urban centers in the world were built on the shores of waterways. In only a few centuries of demographic and industrial explosion, these waterways, once pure and salubrious, have become so polluted, they are dangerous. Yet still today, it's far from these rivers and waterways that we draw the water that flows from our taps. How is it that we are able to drink it, use it to brush our teeth and cook our food? It's because it has undergone shock treatment. It is purified in a filtration plant before flowing through a gigantic network of underground pipes to your house. Our very existence depends on a colorless liquid, water. To survive, we must consume water continuously. Water accounts for 67% of our weight and constitutes 90% of our body volume. Worldwide, the quantity of water being consumed is steadily rising. But the quality of water, well, it is steadily declining. To supply their residents with acceptable drinking water, major cities have installed filtration plants. These installations use various procedures to eliminate pathogenic agents from the water and to improve its color and taste. Here, for example, crude water is drawn from the central part of the river, where the current is the strongest. It is gathered in concrete lines attached to the riverbed. It is then sent along a descending line that carries it, by gravity, toward an underground basin. The bottom of the reservoir is slightly lower than the riverbed. When it reaches this first basin, the crude water goes through a rough preliminary filtration called sieving. It then passes through a grate composed of vertical bars, which eliminates large-sized waste. Next, the water is aspirated by enormous pumps, which bring it up into a canal located several meters above ground level. Through gravity, this canal carries the water to the plant. The water is directed toward a gallery of 60 identical filters. Each filter receives an equal amount of water to treat. The filters consist of 2 tanks. Both are filled with a 1-meter thick layer of silica sand and a thin layer of gravel. The filters work 2 ways. By simple physical action, the sand and gravel capture a portion of the particles in suspension in the crude water. The filters have also been biologically conditioned. That conditioning enables them to digest the organic matter, such as fecal waste, present in the water. For a flora of microorganisms called zooglies develops around every grain. Zooglies feed on pathogenic bacteria and organic matter in crude water. Little by little, the filters become plugged with the matter they have entrapped. They are then all cleaned to restore their filtering capabilities. This biological treatment removes 80% of any coliform bacteria, water's main pathogenic bacteria. It also lessens the turbidity of the water, that is, the amount of matter in suspension in it. Ozonization completes the treatment. It consists of injecting air bubbles containing a high concentration of ozone into the water. Ozone, a gas, is produced by subjecting oxygen in the air to high electric tension. Ozone, whose molecules are made up of 3 atoms of oxygen, has powerful disinfecting and oxidizing properties. It kills any bacteria it comes into contact with. In addition, it oxidizes organic matter. That is, it partially transforms it into carbon dioxide and water. It's as if the ozone burned the organic matter in the water. After undergoing ozonization, the water is free of all pathogenic germs. Its color, from the dissolved substances, is also considerably improved. The ozonized water is then sent into a very large basin, where, through evaporation, it loses any residue of ozone. This step is necessary since ozone is toxic when improperly dosed. Chlorination is the last stage in the treatment. Like ozone, chlorine is an oxidizing agent and destroys any bacteria water may contain. However, when the water has been previously ozone treated, chlorination only plays a preventative role. Chlorine prevents microorganisms from developing in the vast network of canals that distribute the potable water to an entire city. In this type of plant, in which more than 1 billion liters of water are treated daily, many precautionary measures are taken. A computer controls all of the stages of the water treatment. Automatic indicators constantly monitor its quality. In addition, the plant includes a laboratory where advanced analyses are conducted. Should the treated water cease to meet public health standards, the population would be notified immediately. In spite of all these precautions, doubts on the quality of drinking water still persist. Modern filtration plants produce water free of any pathogenic bacteria, but they are unable to eliminate all of the traces of the 60,000 chemical substances which may still be in it. The uncertainty concerning the water we drink is the price we pay for having polluted its sources. Periodically, a catastrophe will sound the alarm. We're always on the lookout for the slightest suspicious smell, the slightest unpleasant aftertaste, and buying up bottled water until we find out that it may not be any better. There is nothing surprising about that. The problem of clean drinking water is a direct result of pollution levels. This is why the treatment of wastewater is so crucial. All wastes, whether they be industrial, agricultural, or household refuse, end up in the waterways. So water's natural purifying power is no longer sufficient. Sophisticated water treatment systems are imperative. In only a few centuries, mankind has caused the degradation of one of its most precious resources, water. Tons upon tons of industrial, agricultural, and urban wastes have been poured into our waterways, turning them into veritable open sewers. But there are solutions. Simple and effective techniques can eliminate most of the polluting substances in industrial and domestic wastewater. Treated water can be sent back to the waterways without threat to natural ecosystems. These techniques can be used to sanitize city wastewater. When water has become polluted, it's mostly due to the organic matter it contains. The organic matter can come from fecal matter, as well as detergents or paper waste. While generally not harmful in itself, organic matter pollutes waterways by promoting the growth of algae and numerous microorganisms. Because they consume the oxygen in the water, these algae and microorganisms deprive all other aquatic organisms of the oxygen they require. The amount of oxygen consumed in a water sample serves as a pollution index. The higher the amount, called biological oxygen demand, the more polluted the water. When a polluted effluent pours into a waterway, it causes the algae and microorganisms to proliferate. The water fauna and flora die by asphyxiation. Fortunately, several biological water treatment techniques enable experts to reverse that process. One of the most effective is biofiltration. In a purification station using biofiltration technology, The water to be treated flows by gravity into an underground reservoir situated several meters below ground. A mechanical grate removes the larger fragments of waste. The wastewater is then pumped up a few meters. It comes to a sand and fat removal unit. This unit collects the sand in the water by sedimentation. Scrapers pick up any matter floating on the surface. This matter is mainly made up of fats. The sand and fats are stored and directed toward sanitary landfill sites. The pre-treated water is then sent toward outdoor basins where it undergoes a primary clarification. By simple gravity, the clarification process allows part of the tiny particles of organic matter still present in suspension to settle. The clarification basins here have numerous inclined tubes that accelerate the sedimentation process. After remaining in the clarification basins for a half an hour, the water is sent along to the biofilter, where it undergoes a secondary treatment. The biofilter consists of 10 tanks filled with grains of porous shale. These porous shale grains filter out the matter in suspension. They also serve as a support for a biological mass, or zooglia, capable of digesting the organic matter still dissolved in the water. A small rotary barrel periodically cleanses the filters to rid them of accumulated solid wastes. The solid matters collected during the cleansing of the filters are combined with those of the primary clarification and undergo a special treatment. First, they are thickened, then sent to a strip filter that extracts most of the water in them. Then the resulting sludge can be taken to a landfill site. Following the primary and secondary treatments, the treated water's biological oxygen demand only reaches 1/4 of that of crude water. The effluent can then be safely released into a waterway. The residual organic matter in the effluent will be eliminated by the waterway's natural purifying power. However, this kind of plant does not purify wastewater of inorganic chemical substances. These substances, such as heavy metals, are discharged by a large number of industries. Harmful even in very small doses, they represent a serious health threat. However, it is possible to get rid of these wastes. Heavy metals, for instance, and other chemicals such as chrome, nickel, and cyanide can be eliminated from industrial effluents through chemical processes. The water is treated in a reactor in which a chemical substance has been poured. The resulting reagent has the property of sticking to the heavy metals dissolved in the water. The latter then settle at the bottom of the decanter, where it forms a metallic sludge. The sludge can be directly recycled into the industrial process or recovered in the form of a solid metal or a metal salts solution. The water itself is cleansed of its toxic compounds. It can be safely returned to nature. We've reached the point where we have to wash our water. The production of dirty water has to be reduced, if not stopped. Better not to soil rather than have to clean up. Obviously, what motivates companies to develop non-polluting production technologies is profitability. Now ecology rhymes with economy. We're beginning to listen to the people we thought were dreamers. We're even starting to think about waste as a resource, a gold mine, in fact. What can we do with all those mountains of old tires? Well, it seems researchers have found a solution that is both radical and profitable. Pyrolysis under vacuum. When archaeologists of the future study our civilization, they will probably conclude that it was the age of waste. sad testimony to our insatiable need to consume. Mountains of rubbish are strewn all over our planet. On top of being hard to conceal, these eyesores pose a real threat to the health of mankind and the equilibrium of the globe. And yet, our wastes are actually resources. Indeed, most of what we use can be used again, that is, recyclable. Large-scale recycling would solve numerous ecological problems, stave off the wasting of the Earth's resources, and even generate profits. Today, almost any waste can be recycled. A new technique has been developed whereby materials as diverse as old tires, oil residue, wood shavings, and household refuse can be recycled into useful compounds. This promising new technique, developed by a Canadian researcher, is called pyrolysis under vacuum. Pyrolysis is a chemical process that causes organic matter to decompose. Organic matter being any substance mainly composed of carbon and hydrogen. Most organic compounds are made of long chains of atoms of carbon, hydrogen, oxygen, and occasionally other elements. Pyrolysis consists of heating organic matter moderately in a reactor in the absence of oxygen. Under these conditions, the chains of carbon atoms first begin to vibrate. Then they break into smaller molecules. Thanks to a vacuum pump connected to the reactor, the little molecules can be recovered. They are aspirated by the vacuum pump, then condensed when they leave the reactor. This process yields light compounds such as pyrolytic oils, waxes, water, or coal. All these compounds are reusable. This technique seems a far better solution to waste disposal than traditional incineration. In an incinerator, wastes are burned at very high temperatures. Moreover, they are exposed to the oxygen in the air. Under these conditions, the organic molecules combine with the air's oxygen to form steam and carbon dioxide. The organic matter is therefore almost completely destroyed. But some organic molecules react among themselves to form toxic compounds such as polycyclic aliphatic hydrocarbons, which have carcinogenic properties. Moreover, incineration produces large quantities of volatile ashes, and they too can be toxic. Even the carbon dioxide released into the atmosphere by incineration has harmful effects on the environment. Its molecules absorb the sun's infrared rays. This generates a greenhouse effect liable to cause global warming. Conversely, pyrolysis under vacuum creates little carbon dioxide and no toxic compound. Furthermore, it takes place in an airtight reactor. None of the reaction's products are ever released into the atmosphere. One of the most promising applications of pyrolysis under vacuum is the recycling of oily wastes. Oily wastes, a result of gas refining, pose a serious threat since they can infiltrate into the ground and underground water expanses. At present, it is both difficult and costly to get rid of them. Pyrolysis under vacuum converts these wastes into usable, environmentally safe compounds, such as oils, water, and clean gases. The toxic compounds in them, such as heavy metals, are trapped in a solid waste. The waste can be buried without any danger of it contaminating the soil. In addition, the energy the reactor requires can be obtained by the combustion of the oils created by the process itself. The pyrolysis under vacuum of gas sludge costs 10 times less than the traditional methods of disposal. Another promising possibility for pyrolysis under vacuum is the recycling of old tires. Tire dumps are time bombs for the ecology. Up until now, there was no way to get rid of the tires without damage to the environment. On the other hand, pyrolysis under vacuum destroys old tires and generates useful compounds such as heating oil, carbon black, synthetic fibers, and steel. Researchers are also trying to apply this technique to recycling urban waste and wood shavings. The latter could produce highly valuable aromatic and pharmaceutical compounds. Pyrolysis under vacuum demonstrates that protecting the environment is not as expensive as some would have us believe. Like other recycling methods, pyrolysis might lead to a new industry that would create profits, jobs, but not pollution. A few years ago, a generation of artists working with refuse took their place in the art world. We saw everything. Performances in the middle of trash cans, installations of old car bodies. These artists were trying to awaken people to what has become an emergency for the whole planet.